Good day students. In this video lecture we will be seeing some of the steps of K-means algorithm in detail. So let us start with the assigning points to the closest centroid. So when we talk about assigning the points to the closest centroid, how to do that, what measure should be used, what are the other things to be considered, uh, that becomes a major concern. That is why we are discussing that particular step over here. So to assign a point to the closest centroid, we need a proximity measure that quantifies the notion of the closest for the specific data under the consideration. As I have already described in the earlier video lectures, in that proximity measure may be calculated using the Manhattan distance, Euclidean distance, Minkowski's distance and all. So we have to quantify that notion of the closest. That's why we are going to see how we can do that. So Euclidean distance is often used for data points in Euclidean space, while cosine similarity is more appropriate for documents. You need not worry what do you mean by the Euclidean space. Usually what happens means the data objects or data points or the records which are given for you in the unsupervised classification, we consider it in the n-dimensional space. So it is very hard to do the computation in the n-dimensional space. That's why we bring it to the two-dimensional space and we call it as the Euclidean space. So that is what Euclidean space, that is L2. Euclidean distance is L2. Euclidean space means that data objects where we are going to consider. So cosine similarity, again this we have already discussed, it is more appropriate for the documents to check the similarity. There may be several types of proximity measures that are appropriate for a given type of data. For example, say that Manhattan distance L1 can be used for Euclidean data. It is by taking the absolute difference between the 2 points we do that. A Jaccard measure may be employed for the documents. This is also seen earlier in the module 1. What do you mean by Jaccard measure, simple matching coefficient on and all. Those who don't know regarding the Jaccard measure and simple matching coefficient, you can go back to module 1 and refer what do you mean by that. You see, usually the similarity measures used for K-means are relatively simple, since the algorithm repeatedly calculates the similarity of each point to each centroid. But in some cases, when the data is in low dimensional Euclidean space, it is possible to avoid computing many of the similarities, because if we avoid the computation, it will speed up the K-means algorithm. And there is another approach also where we can bisect the K-means and we can reduce the number of similarities computed. So this is regarding assigning the points to the closest centroid. Next we will see regarding the centroids and the objective functions which we are going to define based on this. So centroids in the clusters can vary depending on the proximity measure for the data and the goal of the clustering, because goal of the clustering depends upon what kind of data you are analyzing and what is the ultimate result you want. So the goal of the clustering is typically expressed by an objective function that depends upon the proximities of points to one another or to the cluster centroids. For example, minimize the square distance of each point to its closest centroid. This may be one of the objective function. You are minimizing the square distance of each point to its closest centroid. If you are minimizing that, it will be more similar. So the key point is, once we have specified a proximity measure and an objective function, the centroid we should choose can often be determined mathematically, because in terms of formula we can describe and we can put it in a formal framework, mathematical framework. So let us see what kind of data can be there in Euclidean space. Consider the data whose proximity measure is Euclidean distance. for our objective function, that is minimizing the sum of squared error, which measures the quality of a clustering, we use sum of squared error, which is also known as the scatter or scatter, how much it is dissimilar from that point. uh, if we minimize that, the point will be more similar to the centroid. So we calculate the error for each data point, that is the Euclidean distance to the closest centroid, then compute the total sum of squared errors. So given two different set of clusters that are produced by two different runs of k-means, we prefer one with the smallest squared error. It is very simple. Squared error means you just compute what is the actual centroid, and whatever the point you are having, you square it and take the difference. That is the sum of squared error. So here here the table is given, which provides the notation for formally defining some of the terms in clustering. So the X means a particular object, that is the data object, capital Ci, that is uh, Ci, that is the ith cluster, that is C subscript I means ith cluster, small ci means the centroid of cluster Ci, small c centroid of all the points, m mi, that is the number of objects in the ith cluster, m subscript I, m means the number of objects in the entire data set, capital K means the number of clusters. So the SSE is formally defined as follows, that is sum of squared errors. You take the summation of all k clusters, that is I is equal to 1 to k, then you take each objects in each of the clusters and compute the distance from Ci, that is the centroid of each cluster, and remaining data objects in that particular Cith cluster. That's why I earlier told you, it's very simple. From the centroid to the data points, you compute the sum of squared. That you do for all the clusters, which will give you the sum of squared errors. Only thing is, you need to remember the notation. K means the k number of clusters, capital Ci means it is the Cth, that is Cith cluster, small ci means the centroid of the cluster Ci, x means a particular data object. These notations you need to keep in your mind. So given these assumptions, it can be shown that centroid that minimizes the SSEs, that is sum of squared error of the cluster, is the mean. It's very simple to do that using the notation in the table 8.1. The centroid, the mean of ith cluster, is defined by the equation, you take all the points, that is x belonging to Ci, divided by the total number of objects in the ith cluster, that is the mi. So we can illustrate it using the three two-dimensional points over here, that is 1 1 comma 2 2, not 2 2 2 3, and 6 comma 2. That is, you add up that 1 plus 2 plus 6 divide by 3, because 3 objects are there. 1 plus 3 plus 2, 3 objects are divided by 3. So you will be getting the centroid of the cluster as 3 comma 2, which is the mean of the particular cluster. So steps 3 and 4 of the k-means algorithm directly attempt to minimize the SSE. Where is this steps 3 and 2? That is this one we are talking about. Steps 3 and 4, form k clusters, recompute. All these are actually seeing to minimize the sum of squared errors. Step 3 forms the clusters by assigning the points to the nearest centroid, which minimizes the SSE of the given set of centroids. Step 4 recomputes the centroids of so as to further minimize the SSE. Let us see regarding the document data and the general case, and we will end this. K-means is not restricted to the data in the Euclidean space, but it is also possible to consider the other type of data such as document data, which uses the cosine similarity measure. Here we assume the document data is represented as a document term matrix. This particular document term matrix representation we have seen in the module 1 when we have seen the different types of data where we represent the documents in terms of the matrix. Our objective here is to maximize the similarity of the documents in a cluster to the cluster centroid. The reason is we want the document to be more similar. That is why we are maximizing the similarity, minimizing the distance. This quantity is known as the cohesion of the cluster. For this objective, it can be shown that cluster centroid is the mean. The analogous quantity, which is of the total sum of squared error, is the total cohesion, which is given by this particular equation. This is similar to the total SSE, where we are going to consider the k clusters object in a particular CIth cluster. Then you take the cosine of a particular xth object with the centroid. So that is the formula for the total cohesion. So the general case is there are a number of choice for the proximity function, centroid and objective function that can be used in basic K-means algorithm, which are guaranteed to converge. So table 2.2 is going to show that which are the other proximity function, centroid and objective function we can take into consideration. So the proximity function may be a Manhattan, centroid is median in case of the Manhattan distance, objective function is minimize the sum of L1 distance of an object to its cluster centroid. Similarly, squared Euclidean we have already seen, cosine, Bregman divergence it may be. For Manhattan distance, the objective of minimizing the sum of the distance, the appropriate centroid is the median of the points in a cluster. How does the median differ from the centroid? Median means the midpoint of the set of points you are going to consider. If you are having the even number of points, then you take the median of those particular points, and if you are having the odd number of points, you can take the median. So it all depends upon how you are going to compute. So here we will end regarding the discussion of the steps of K-means algorithm. Then we will see how to choose the initial centroids and how the poor choice of initial centroids will create a problem for us. All those things we will see in the future lecture. Thank you.